greater intelligence, kind of like Superman.
Oh, of course.
Yeah. So that's a strength thing. This is more of a. I mean, he's fat, so he's the same level of fatness. Although I think his stomach teeth have become sharper on Mars. I don't know. I can't really tell you what that's attributed to, but it's
Electromagnetic effect.
something. Yeah. Right. What happened? What is? The stomach guy? Just real quick, I'm just thinking about something here. Let's go back to the scene. I want to click on him. No, I need to go back to the code. I want to know if we can.
Is that like the default character, or did you select?
No, you could select all sorts. You have dragons and baby yetis.
Sasquatch with a mouth for a stomach.
Right, that's the one we picked. What I was interested in here is because you can grab all sorts of
Elvis?
yeah. Yeah, you can grab the middle finger. So these are all like for doing 3D animation stuff. I was thinking you. So here's get mouth. I wonder which mouth. Does he have the extra mouth? No, he doesn't. It's visual only. It looks like, unfortunately.
Or is that the mouth that's talking about?
Yeah, maybe that is.
Oh, no.
That would be awesome if he opens his mouth. Then we'd probably release that game as some sort of children's game.
Have you looked up Mapengari fights? It's on Vimeo.
A Mapengari fight?
Yeah. Somebody made a little animation fight in Alice.
Oh, I see. All right, so let's go into our code here. All right, so right now our copy what's the I have too many things. Okay, so what happened? Is that a huh? What happens in this thing? Just give me the summary.
Just a fight?
Well, you say it's pretty funny. Well, no, I mean just
like 1 minute long.
Give me the 5-second version. There's a fight. How are they fighting?
I don't have words to explain it.
There's not like weapons or anything?
Where is this?
The only way to describe it is in Bolivia, and we don't speak it.
All right, shut up. Well, let's figure out the deal here, and then I want to go on to our next stuff. Then we looked at Universal I/O. Okay, so I don't believe the problem. Well, actually, let's just for the sake of argument right now, let's make sure the problem is in our output file. So we're going to do print. Get char at index. argv at bucket 1. So this should print it out to the screen, right? We'll go ahead and this is copy reverse. Oh, this is print F is what this should be. Okay, that's just the memory address thing. That's fine. There's an error in there too. No, these are both warnings. Okay, so we're going to run this. We don't even need to give it a second parameter, but we will for right now. Oh, well, what?
You did A.out, didn't you?
Yeah. No, hold on.
Yeah, and you didn't change the arc thing again, didn't you?
Who?
Isn't that the problem?
Yeah, I'm saying arg at bucket 0.
No, you want to say 1, don't you?
I was rather 1. I'm saying 1.
Yeah.
I mean, we don't even need this second parameter here. Oh, that's not going to work. More copy dot c. All right, that's a legit thing. Let's compile this guy again. argv is the oh, hold on. I know the problem. I'm writing bad C.
What?
I'm writing bad C code.
You want to say that one more time?
I'm writing bad C code.
It's on the recording.
This needs to be a %C. Because this is coming out as a char pointer. So it's printing out memory addresses. That's what I'm telling it to print out, right?
He's gonna actually spend some time in this video. It's gonna go on YouTube, like edited as YouTube footage.
Get char and index. Oh, this is a %P. We're going to get this right one of these times. So that's actually the memory address. That comes out as a char pointer. Are those all the same? Those are all the same. Just that same warning. So there's our char. I'm returning the value of buff. But really, it should be buff at 0. It should be the same thing.
No, did we go over that the difference between those two was like doing just the buff was the same as doing the ampersand.
Okay, so this should be just a C. There we go. There we go. Okay. So that guy looks legit now. So now we should be able to do the write. Seems like I would have been better out there. Copy, copy. Did I already? Save. This guy comes out as an int. We're writing what does write take as a parameter? We turn it into a char there. Oh, argument is of type. Oh, so shouldn't I have been able to do the address? The address of all this crap? Or do I actually need to have the guy return? I do. So this is going to return a int pointer. So with that in mind, I should be able to just return buff. I say get chart index, this should allow me to go through, fill up buff, ultimately return buff at bucket 0. That's going to get me a character. Great. So now when I go to write something out, the write function, this is a char, but the write function requires a char array. So we should be able to do this then if we're going to fake it. Should be able to say char answer buff size like that. I should be able to say answer at bucket 0 is equal to this. And then I should be able to just send answer in here. All right, there's copy, copy. All right, that looks legit there. So now I should be able to do copy, copy to copy, uncopy. And that should give me my correct order. All right, I'm missing one double. Okay, I think that was the thing we changed at the end last time. All right, so that's.
Doesn't like it.
That's hold on a second.
Doesn't like it if you reverse it, and then reverse it again.
There, that should do it. Copy, 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 uncopy. So here's copy, uncopy. That.
Give an extra.
Okay, is that an extra?
Yeah.
Okay, so that would be the very.
And then you have two hashtags.
It's repeating the very last character.
Yeah. No, well, there.
Oh.
Go to your copy reverse. And numb bytes. What's that?
Well, hold on. So the issue is this. That's going through an extra time, but the first value I'm getting is I is equal to num bytes. That's what I want. Copy, 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 uncopy.
Where's copy?
Are we sure that wasn't just me?
I think that actually was there.
Copy, uncopy.
But is it in copy or no? Remember we put that Q there because it was no, in the actual copy.c. No, it's copy reverse.
Oh, I understand what you're saying.
Yeah, we actually
We
put
did
that
it on
Q
purpose.
down, yeah.
So it should be correct.
Yes, that was correct. We should have done that.
There's copy, copy, and copy, uncopy. And if I write copy, uncopy, this should be in the right order. Does that look right? That's right. No extra little flippies. All right, so what did I do? Get num bytes returns an int, which is the type for a byte. We were trying to do char pointer stuff last time, which I think maybe is dangerous and maybe what was causing our issues. So get num bytes is returning a, well, that's num bytes. This guy up here, get char index, is also returning an int. What int is it returning? It's returning the integer at bucket 0 of buff. Okay, even though buff is a char array, chars are integer types, just like they are in Java. So this guy's coming out as the first integer within this guy. That's what's going to get returned there. What did I do? I went ahead, and since this guy was coming out as an int, I couldn't use him with a write. I could do it with our print here. But what I did is I just created a array of buff size. So I had one bucket, and I just kept setting that guy at bucket 0 equal to the new character that came in. And then I would just use this guy to write out. Make sense? So I think that will, as we've seen, there's probably 20 different ways we can do this. As I was looking through the assignments, I think some of you used Lseek versus Fseek. So what's the difference there? So last time I purposely said I wasn't going to use the F stuff, okay, for vulgar Christian worldview reasons. No, so I mean, what's the problem with like fprint, fopen, fread, fwrite, fseek? What's wrong with those things in the context of what we've been discussing?
That's not universal.
Yeah, they're specific to files. That doesn't mean it's wrong. It actually probably means they're better. It probably means they're better for working specifically with files. But we're trying to harp on this idea of POSIX universal I/O, where we can use opens, reads, and writes with anything, regardless of what it is.
So let's say you ran this program on a thumb drive you have. Would it what would it reverse? Would it be a text or
Whatever it was able to read in.
whatever?
Yeah. When we did a read on it.
Flash drive or something?
Yeah, so right. I mean, so this will reverse whatever we send it.
But doesn't it consider everything as files?
Well, but what does that mean? I mean, last time we saw that we accidentally read in from our A dot out, right? When I put a bucket 0 instead of bucket 1, that's binary data. Was perfectly happy reading it and perfectly happy destroying the console because it was writing binary data out. So yes, it treats everything like a file because everything in our computer, whether it's binary data or whatever, is a file, right? It's a container for data. It'll read data in from a text document. It'll read data in from a binary document. It'll read data in from, like he pointed out, a USB drive. Anything that we can connect to through a file, we can open and try to read from. Make sense? I don't know why. A very funny, I want to say funny, but I'm almost kind of like embarrassed to say it. A phrase from a movie popped into my head as we were doing it from, was it the original Meet the Parents? You know, when he was talking about cats, anything with nipples you can milk or something. Why does that pop up in this context?
I have a file, Greg. Can you reverse me?
Like I feel like it's related, but it shouldn't be. This all has stemmed from me having lunch with Amish today. The whole rest of the day has been out of sorts. Sorry. It is what it is. All right. So yeah. So in any case, we were talking about Lseek. So Lseek is a much more generic version of fseek, right? Fseek assumes that we're dealing with data files, with ASCII files, where Lseek literally moves in an offset within a file, not really making an assumption what the contents of that file looks like. Okay, so let me get to our next stuff. Create system call really isn't used anymore. We used to use it. Open used to not automatically create a file if it didn't already exist, but now we have all those flags like create and that kind of stuff that we can send in, so the create function isn't really used anymore. Let's seek. Okay, so now we're back to kind of file I/O, not file I/O, we're operating system level stuff, specifically talking about inter-process communication using files for sharing stuff between two processes, for example. And one of the weaknesses that we have is this idea of, one of the weaknesses we have is this idea that a file can be read and write from two different processes, correct? And we want to kind of prove that initially. And we're going to do this by finally, after all this time, Abe. We're going to fork a child process. Okay, we're going to finally do that. How was your job interviews yesterday, by the way? Did you get hired?
Got a couple well interviews.
So no.
Emails?
Yeah, nothing. Doomer? Yeah, anything?
Got a couple,
So no. Got nothing.
nothing yet.
All right, keep me informed. All right, so let's go back out here. So, you know, where chapter 5 is getting into is this idea of atomically, what is it? Atomicity? Atomicity?
I don't even know
What does it mean for something to be atomic? Let's go back to
Can't be interrupted.
can't be interrupted. It happens as if it's in one CPU cycle, that stuff, right? So we're going to be dealing with ways that we can lock down a file for either read purposes or write purposes or both, that kind of stuff, if we have two or more processes competing for that same file. All right, so we want to start.
So are we talking like file locking?
Ultimately, that's going to be one of the inter-process communication things we're going to look at first. But before we do that, we need to be able to fork some children. It's like, don't you forget it. All right.
Dreams are coming true.
So let's go back here. So I'm gonna do. We're gonna do a man fork. Ay, ay, ay. All right, so fork creates a child process. So the fork command creates a new child process, a new process by duplicating the calling process. The process referred to as the child is an exact duplicate of the calling process referred to as the parent, except for the following points. Was that phrasing? I missed it?
Show the points.
Oh, just all right. Child has its own unique process ID. We've discussed that, right? The parent ID will, I think, return a 0, and we can see that here in a second. In fact, do we just want to do that? This guy lives in Unix standard.h, so that's the guy we're gonna need. And notice the synopsis. Here's the header of that function. So fork takes in nothing and returns a process ID type. So this guy is, what kind of animal is this guy based on what we've learned up to this point? Cat, dog, or struct? Pebbles. You just, I gave you 3 options. Cat, dog, or struct? Is that really too small? Is there a way to make this bigger?
Remember that cat is actually a method.
But see, I think it's giving me a view into their console. It's not just text put on there. Yeah, there might not be. Oh, whatever. Okay, so it's a struct.
Actually,
It is a struct.
Back out of there. Like minimize it.
Oh, you want me to get back out to the...
No, just make it smaller.
Oh.
And now do Command plus a couple of times, and now blow it up on the bottom.
No, I understand. Is that better?
Yeah.
Is it? All right, so it has to happen at this level. And that's going to be unusable up there, but whatever. Is that even?
Yeah.
All right, so we'll... what used to be blades. So we manned fork again. All right, so this guy returns a struct type, which is a actually it is a struct, but it's actually just going to be a synonymous data type. So this is probably just an int, PID underscore T. Man, PID underscore T. Do we get one of those? No, we don't. All right, so in any case, the child's parent process ID is the same as the parent's process ID. Yeah, here's some of the important stuff we'd already talked about. The child does not inherit the parent's memory locks. We don't know what those are, but we talked about them at the high level. So anytime when a process creates memory for shared memory, a child process would not get access to that same thing. We would need to take special care in order for a child to be able to talk to its parent directly. Process resource utilizations and CPU time counters are reset to 0 in the child because this is a brand new process, as if we had double-clicked a Microsoft Word or something like that. He's not sharing. He's not a thread. He's not sharing the CPU time with the parent. The child's set of pending signals is initially empty. So these are the things that the child might be interested in knowing about. Right? So the idea is and we haven't dealt with signals yet either. We're kind of moving towards this inter-process communication stuff. But if we are the parent process and we've registered to become aware of 5 different signals, when 5 different events occur, that's what a signal is, right? And we spawn off a child, by default, the assumption is that child isn't interested in automatically being notified about the same signals the parent is. More than likely, the child is being spawned off to do something brand new, unrelated to the parent, as a worker bee. So the child doesn't participate in all those things either. Let's see. The child does not inherit semaphore adjustments from its parent. So if a child is spawned off and there is a local semaphore, the child gets its own copy of that semaphore that protects its own resource. It's not in the middle of the any changes to that semaphore from the previous thing. Record locks. These are all kind of the same thing. All right, so let's go ahead, Abe, and let's fork some children. All right, so this was uni. Let me grab this real quick just so we have it. And let's go there. All right, so let's go ahead and let's close all these things. And we're going to create a new file. We're going to call this guy fork test. I just about came up with a better name, but we just about went with child forker. Christian worldview. All right, so we're going to import or include uni_standard.h. We're also going to include standard.io.h. We'll do int main int argc char pointer argv. See, some of the C stuff's coming back now. So in any case, let's go ahead and we'll print something out. So print f the original. All right, then we'll go ahead and we're going to do a who? What? Oh, well, I don't want the brackets. I want that. That's what the cool kids would do. The C++ hybrids would do the brackets. Cool kids do this, right? So in any case, we'll print out the original here. Then we're going to say PID underscore T PID is equal to fork. And then we're going to say printf. My PID is, I think it's going to be just a decimal. PID. Just leave it like that. All right, so we'll see if this guy builds. All right, so we'll do gcc forktest.c. All right, and we'll just do a.out. The original my PID is, this is the new dude, and then the original my PID is 0. All right, easy as that, Abe. Just forked a child. All right. You know, you do realize at some point the police are going to come in here. Just campus safety hears rumors. We heard about somebody forking children in here. Like, whoa, you have it wrong. Okay, so we are able to determine whether we're the parent or the child. So we could ask the question now: if PID is equal to 0, printf, I am the parent. Else, I am the child. My PID is that. All right, so we can do 2 separate tasks depending on whether we're the parent or the child. Build, compile. Here's the original. I am the child. My process ID is this. I am the parent. I never actually printed out the process ID for him, but we're able to differentiate between the original and the other guy. Okay. So now let's go ahead and let's do a loop that prints out some stuff. And hopefully we're going to be able to see the scheduling. All right, so we, well, about to fork. And then the parent, we'll just do it inside. So we're going to say for, I'm just going to do it. 0 I is less than 100, I plus plus. So we're going to say parent colon percent %d slash I. So that's what we'll do if we're the parent. This is what we're going to do if we're the child. Child will have in parentheses their process ID and then an I. All right. I wonder what happens. Does it recognize that it has to compile that if I run it? No, it doesn't. What has happened?
Yeah, C99.
Huh?
It's because you're declaring I in for loop.
Well, no, this is something else. Oh, here's my, this is the, that was just the error output. Oh, well, that's the other problem, yeah. Doesn't know about that in C99 by default. Okay, whatever. So we'll let both of those guys, they'll both get a copy of this variable, so they'll both be able to use it.
So is that just a syntax thing that it needs the semicolon in the for?
Correct. For loop requires 2 semicolons. So now I should be able to GCC this, ./a.out. All right, let's. All right, so we did see a little bit of scheduling in here. So we saw that we had some child, some parent, some child, some parent. And then we had a big long string of child counters. But what we're seeing visually here is CPU scheduling, right? Because each of these, we're probably seeing CPU scheduling. We're definitely seeing CPU scheduling. It's possible, though, that these guys aren't bumping each other off of the same CPU. Because more than likely, whatever Cloud9 is using is not a single core CPU. But it is possible that they've only given us a single core CPU for part of our system resources. So it might actually be a single core CPU. All right.
I don't know.
If we do a top, does it tell us what
Doesn't make sense to me, but
top CPU? Yeah, I don't know. Because this says CPU sleep use. Here, let's look at what top looks like on the Mac. Yeah, it combines CPU usage under a single umbrella, so it doesn't really tell us. Well, you can probably see one of the, because your CPUs probably have their own output files and /opt maybe, but I don't want to screw with that right now. Okay. So now that we can create child processes, what types of things might we do with a C program that can fork children based on what we've learned in earlier courses? Why do we split processes? Why do we spawn off child processes? What's the advantage?
Should CPU time for the children.
We test more efficiently.
Okay, what kind of tasks?
That a lot of things need to happen, but they're not necessarily super interconnected. Like you don't have to do one, then the other, then the other. You can just do a bunch of them.
Huh?
He's saying for the type of problems that are you're able to that aren't interconnected, like the cleaning the park scenario, like you don't need, or like
You don't need to know what the second guy is doing.
yeah.
Yeah, it's just rand from standard lib. Make sure I give you enough stuff here to do this impossible homework. Actually, it's going to be a double, I believe, that comes out of standard. Ay, ay, ay. I don't like this whole code in web browser thing.
I think you were the one that decided we were going to use that this year.
No, I'm not used to the flipping back and forth thing.
You just have two web browsers open.
I don't know how you live with that many tabs open. I would literally go insane.
Like
With
5 different
last
ones
two
you do.
tabs open.
Okay.
Most of it's from 518.
Yeah, well, it does return an int. That's interesting. I thought it returned a double. Well, that's going to make this even easier. So int num is equal to rand, and then we'll do a printf. So let's do this.
It's not gonna like that, is it?
Yeah, we'll be fine with this. Printf %d.
Yeah, those have to set it back to 0.
Say this again.
In I for the other if the ID.
Oh, because I have it down here.
If you just
I got it. I thought you were talking just in the context of this here. All right, so what? Actually, let me. So this should generate 10 random numbers. Oh, let me do the back. That is ridiculous. All right, so there's my 10 random numbers, and what we're going to do, and they all are, looks like positive numbers, right? Let's just make sure we didn't get lucky. Yeah, nobody's that lucky. Okay. So it's positive numbers. So now we'll do mod 2. So that's random zeros and ones, 10 random zeros and ones. All right, so now what we're going to go ahead and do is we're going to have a int nums size 10, and we'll say nums at bucket I is equal to that. And then just to prove that it worked, we'll steal this, go right below it.
What? Num at bucket I thought num was an int.
Nums. And we're going to print that guy. So this should create an array capable of holding 10 integers. It should then fill up that array with 10 random zeros and ones, and then in a separate loop it's going to go through proving the array is filled up. Okay? So we'll go ahead, compile, run. All right, well, the array is filled up. That's same output, but it is, you know. Here, we'll put some woots in front of that. All right, so that's the contents of our array. All right, homework assignment is now that we have 10 random zeros and ones, what we want to do is we want to write a multi-process implementation of merge sort. So merge sort is a divide and conquer sorting algorithm that we learned in 300, right? Actually, we learned merge sort in 250. Okay, remember the recursion guy? Okay, except now every single time that you do a divide and conquer, you're going to spawn off a brand new child process to go and handle that sublist. Make sense? So you have your original process that says, is this sorted? The length is not 1. End is not equal to, or begin is not equal to end. Therefore, we need to split it in half, sort the left side, sort the right side. Historically, we'd make a local recursive call. But what are we going to do now? We're going to spawn off a child process to sort the left and a child process to sort the right. Worker bees. The left child process is going to go among and keep doing his work. Okay, and what's he going to do? Okay, what's he going to do? Say this again.
Isn't that exactly what we do by doing recursion, though?
Except that's happening within the same process. We're doing this across multiple processes.
So this is just using processes instead of threads.
Yes, but what limitation are we going to run into here? I have a single array called nums right now. And didn't we see a limitation of fork? Our child processes, they're going to get a copy of the variables. Will they get the same memory, the same array to be able to write into it? Does that make sense? So, you may have to use only the tools that we've been introduced, some file I/O, to keep track of what individual processes know about. Make sense?
No.
You know what merge sort is, right?
Yeah.
Implement merge sort with multiple processes.
On what? What is our end goal?
Sort zeros and ones.
From like random.
Here's 10 zeros and ones. Sort them using a merge sort.
Okay.
That's terrible. How are we gonna know? That's terrible.
Well, if you don't want to have zeros and ones, you can make it non-zeros and ones. But that's a good test of sorting algorithms. You sort zeros and ones, it's accurate. So if it'll make you feel all nice and warm and fuzzy to not have zeros and ones, that's fine. It should make a difference, right? All right, so every single time you would have made a recursive call, instead you're going to spawn off a child process and tell him to sort part of it. All right? I will, and that's due on Friday.
Wait.
What?
You text Slack.
Like right now?
Yeah, right now.